Welcome everybody to the Michael Rossmann Legacy session. This is a very special event, and the idea is to celebrate Michael's legacy to crystallography and maybe a little bit EM, since that's a big part of this meeting also. And we have 5 speakers who were alums of Michael's lab, and they are going to go in chronological order. But first, I would like to introduce some members of Michael's family. We're very pleased to have with us his wife, Karen Bogan. Karen, could you stand up? And Heather and her husband, Dennis, are with us. To greet them at the reception after this session. So our first speaker is Jack Johnson.
It's very nice to have such a large group of people here to recognize Michael. He was born July 30th, 1930 and died on May 14th, 2019. I just wanted to point out a few aspects of this remarkable life that he had. He had about 200 graduate students and postdocs, and in 2017 we had this marvelous symposium at Purdue to celebrate the science that had gone on there. He was elected to the National Academy in 1984, the Fellow of the Royal Society in 1996. He received many, many awards. This is just a small sampling of them. He had 612 publications, 6 in 2019, and still counting. I'm actually refereeing a paper right now. And he had 6 honorary degrees from a variety of international universities. His personal attributes, he was energetic, competitive, impatient. Things never happened fast enough for Michael. On the other hand, he was warm, considerate, and compassionate. I had numerous examples where he was very, very thoughtful in my personal and professional life. He had an extraordinarily broad knowledge of history, current affairs. He was an enthusiastic conversationalist on many topics. He loved the outdoors, hiking, skiing. He was skiing well into his 80s. Sailing, he won the Indiana State Championship in his class multiple times. And he enjoyed his family immensely. He was married to Audrey Rossmann for over 50 years, and she preceded him in death in 2009. He was very enthusiastic in his support of her artistic work and provided the muscle for moving things around for art fairs and so forth. And in 2015, he met Karen Bogan, and they were soulmates for 4 years. They were married just over a year ago. And I met them in Portugal, and they were like 2 young kids that had just gotten married. And so that was a wonderful time. So I just want to quickly run through the early part of Michael's career. He was in Cambridge from 1958 to 64. He was absolutely a critical component in solving the structure of hemoglobin with Max Perutz. At 5.5 angstroms, they were able to determine that it looked like myoglobin, and they were able to connect the helices in what turned out to be exactly the right order to be able to solve that structure. During that time, he also developed his ideas for molecular replacement and published this classic paper in 1962 with David Blow that had the essence of cross-rotation functions, self-rotation functions, and envisioned using non-crystallographic symmetry to solve virus structures. He moved to Purdue in 1964. Henry Koffler was the department head that hired him, and Henry wanted to develop a molecular biology department at Purdue, and Michael was one of the first people in that regard. Michael really loved Henry. Henry was actually at our 2017 symposium. He has since died, but that was really a touching sight to see the 2 of them. In 1970, they published the structure of lactate dehydrogenase at 2.8 angstroms. It was one of the largest protein structures determined in that time frame, and was very important for understanding binding of nucleotides and so forth. The group in 1973 included Martin Hackert, who's in the audience, and myself, who was a very fresh individual, and Manfred Buhner and Dino Morass, who were very critical in solving the structure of glyceraldehyde 3-phosphate dehydrogenase. And this structure was critical because I remember coming in the morning after they solved GPD, and Michael had written on the blackboard, GPD is LDH. And they had discovered that the nucleotide binding site in these two proteins was virtually identical. And this was a critical step for developing the concept of the Rossmann fold and this molecular evolution that was indeed looking just like macroscopic evolution that had been understood for a long time. So from 72 to 2019, Michael's love of viruses. Yours truly arrived in the lab in 72. I had significant adjustments. I had no biology, no biochemistry, no protein crystallography. My PhD advisor, who was also Martin Hackert's PhD advisor, was low-key and very patient. Michael was neither. I had to develop a strategy for coping with this that I call danger signals. And I was inspired by the Far Side cartoon that had nature's danger signals, which included this guy with a rubber inner tube and a large bore gun. And Michael never had on an inner tube or a large gun, but we needed to see the danger signals. So I discovered that if we looked at the angle between his head and his shoulders, which we can call theta, this gave a real good indication of what the RDS factor was. And if you just use this simple expression of 1 over the sine theta, you realize when RDS went to infinity, you should run, which I did on a few occasions. So we solved the structure of SPMV and published it in 1980. Someplace in the audience is Stelia Zapatero, who was one of the crucial players in that. And anyway, there were a few things that happened in this process. First of all, we had a really hard time getting structure at high resolution. We would have data to 3 angstroms resolution, and the map would look like it was at 6 angstroms resolution. And Michael was getting more and more impatient with this, and he was blaming me because I had the molecular averaging program. The shoulders were high, and the whole project sort of hit its culmination in a negative sense when we were all gathered around the light box. This was a large light box with stacks of electron density. The electron density was smeared, it didn't look good, and suddenly the entire top of the light box collapsed and went in on all of the fluorescent bulbs shattered, and Michael just went and walked away. And I thought, this is symbolic. We have to get the light box back as soon as possible. So I ran to the shop, and we got the light box back. Turns out we had the wrong lattice constants. That was the whole problem. Somehow or another, some older lattice constants had gotten put into the programs, and when Sugihara came to the lab, he asked Michael, why are we using those lattice constants when the latest lattice constants from the processing are this? And Michael, nobody knows. Anyway, it turns out that when they solved the structure, Andrew Leslie and Michael traced the chain, and Delia was involved, I'm sure as well. Anyway, once again, it turned out southern bean mosaic virus looked like tomato bushy stunt virus, so it was like the nucleotide binding fold all over again. And Michael would get so excited when he was building the model in the Richards box that he would raise up quickly and bash his head. So he eventually had to get a crash helmet to protect himself. This was the group that was there. Felix not in this picture. I think he was in the next one. But anyway, there were some key players: Ivan Raymond, Andrew Leslie, Sugihara, and we had a fantastic group of people that were working on this on southern bean mosaic virus for 8 years together. So I thank you, Michael, and I think that it's fair to say there's widespread respect from all those that worked with Michael or knew him well, and we all have gratitude for how he shaped our life. in peace, Michael Rossmann. And thanks for your attention.
Our next speaker will be Eddy Arnold from Rutgers.
It's really my great privilege to be able to share with you some thoughts about Michael's scientific importance, his legacy, and also some personal reflections that I had. And I am really grateful to Jack for such a wonderful introduction. So here's a picture. Michael was a wonderful educator and inspiration to so many people. Here he is at a meeting that he organized in Sicily. Tom Blundell's on the left. So you've already heard from Jack about some of Michael's accomplishments at Cambridge. Basically, he worked with Max Perutz. He showed up there. A lot of data had been collected following a postdoctoral stay with Bill Lipscomb in Minnesota. And there he just simply had an amazing array of accomplishments. He established the general methodology for isomorphous replacement and anomalous dispersion phasing. He developed the difference-Patterson maps for both isomorphous heavy atom replacement and for anomalous dispersion. And he also, as you heard, developed the concepts involved in molecular placement. Here's a paper describing how to locate heavy atoms and how to refine their positions and shape. This is where he developed the theory for difference anomalous Pattersons. With David Blow, he suggested how to use a single isomorphous derivative to obtain what was called at the time a best Fourier map. And of course it's now SAD that's taken over, but this was SIR, and of course SAR with anomalous scattering is even more powerful, but you can imagine in 1961 that's quite a breakthrough. Also, with David Blow, he developed the first methods of phase recombination using the trigonometric kind of function that was later expanded to make the Hendriksen-Latman phase combination. And, of course, the monumental paper cited on how to use non-crystallographic symmetry to do so many things, to locate the relative orientations, eventually positions with translation functions, non-crystallographic averaging. This is truly one of the monumental discoveries in crystallography and really guided so much of his career. He really chose problems from the very beginning to take use of molecular replacement. And of course, the efforts culminated in the beautiful work that Jack referred to, and Max Perutz, together with John Kendrew, was awarded the Nobel Prize based on these types of accomplishments, really changed the world. This type of approach led to the whole field of protein crystallography. Michael worked from the beginning of protein crystallography until now. There's really no one else who's had that kind of legacy. I happened to be in the lab from 1982 to 1987, just as Michael was really getting geared up to do animal virus crystallography. He was so excited about this. There were a number of technological innovations that were required to accomplish this, namely that the lab had to become skilled in producing animal viruses. Poliovirus was a possibility, but Jim Hogel at Harvard and then Scripps was already working on that. Roland Ruckert helped. John Erickson was one of the key people at the beginning who adapted all of this to work in the Purdue environment. And then we developed a P213 cubic crystal form following an initial orthorhombic form and combining new technologies of synchrotron radiation, supercomputers, and especially Michael's averaging, non-crystallographic averaging, helped to solve the problems just in a really spectacular way. Some progress had been made in what was called phase extension by non-crystallographic symmetry averaging and reconstruction, when Paul had shown that you could go from 3.8 to 3.2 angstroms with a hemocyanin structure, but we were able to go from 5 angstroms resolution with very poor heavy atom signal to 3.5 angstrom, an absolutely perfect map, 804 amino acids in an asymmetric unit, completely connected, and the perfect phases from this non-crystallographic symmetry averaging. I puzzled, how could we ever get the atomic model to approach that? And I thought, and Michael agreed, that using the phases from the averaging would actually give us the best opportunity by using those as observations. So here, at the beginning of this effort with the cubic crystals, we used the walk rotation function to figure out the orientation. Michael and I developed a comprehensive way of thinking about the effect of redundancy as the square root of n, and solvent flattening as an inverse of the solvent content, to put together a concept of how to put this in the terms of phasing power. We also thought about how vector search methods and different Fourier methods were related. We were able to even post-refine the wavelength at a synchrotron source by using very exact data from chess. We cataloged all this information in great detail to share with others exactly how to go about these things. And again, we used the phases as observations. These were some of the technological innovations that drove this effort. And then, of course, the most amazing thing was the kind of biology that we learned from the common cold virus structure. This was incredibly exciting. This was the first animal virus structure. We were able to publish this in Nature about 3 months after getting the complete structure. And of course, poliovirus was also being solved in parallel by Jim Vogel, but we just learned so much about, for example, receptor attachment. How could a human rhinovirus attach to cells and still, have more than 100 serotypes? Michael coined the canyon hypothesis to explain this. We understood a lot about neutralizing antibodies based on the work of Barb Sherry and Roland Ruckert from the University of Wisconsin, close collaborators. Again, we saw that the animal virus code protein was the same as the plant virus code proteins. I refer to this as Michael's leitmotif, because this evolutionary concept that started with hemoglobin and myoglobin, and then the Rossmann fold with GPD and LDH, and then finally with the viruses, was just a remarkable set of continuity throughout his career. We also, with Tom Smith and Sterling Rithrop, drug company, were able to describe drug binding in the site of attachment, and this served as the basis for drug design. Really wonderful work. Implications for assembly, including polyprotein processing. This has a great deal of impact on me, because at this stage of my career, I'm describing the structure of the HIV polyproteins. RNA viruses do this sort of thing. And so these were just amazing experiences that I had. I was also fortunate to publish with Michael a number of crystallographic papers and volumes. For example, Michael was invited to create the first international tables for macromolecular crystallography, and he told me, Eddy, if I can't do this with you, I can't do it. It was an extreme compliment. We put that together as the first edition in 2001, another edition in 2012, just an absolute compendium of articles from all-stars throughout the entire field, a real cross-section. And at the moment, we're putting together a third version led by Liang Tong, and of course, we're dedicating this volume to Michael. And I just wanted to show briefly a few personal pictures. Michael was such an inspiration to people in my lab, so many young people around the world, that they all love to see him. This was in January 2017 at Rutgers. He was a close family friend. Turns out that he loved to go to Lake Michigan, and my family went to exactly the same place. So here he is with my father's sister, my Aunt Betty, in Macatawa, Michigan, on Lake Michigan. He was the Shatkin lecturer at Rutgers University. a friend of Aaron Chapman just in November of last year. Here he is with Karen, his beautiful new wife. And here he is with my new wife, Louise Arnold. And of course, all of you know Stephen Burley. So here in 2014, I was able to visit him at Hockmeyer Hall. He really needed the best kind of CryoEM detector, and I came to help figure out how we could get the funds to do that. And I just wanted to say thank you, Michael, for everything.
And our next speaker is Zhao, who is at Harvard Medical School. And I, again, don't remember. I was Michael's colleague for 18 years at Purdue, and Zhao was a graduate student when I was an assistant professor.
Exactly. Yeah. I thought you were a student. When I first met you, that's what I thought. Okay, right. Thanks to Jack and Eddy for the comprehensive account of Michael's contribution and for revealing some of the intrinsic humor in Michael's personality. It was always a lot of fun interacting with him. So I joined Michael's lab in 1988, and that was after I met him in the year prior as a medical student in Beijing. So having heard his lecture on the crystal structure of human rhinovirus, the one that Eddy just talked about, I was so amazed by the power of this discipline called crystallography, which I had never heard of at that time. I decided to quit medical school and came to Michael's lab to learn this thing. And everything else was history, and that was really the beginning of a career in structural biology. So in my few-minute spiel, I like to focus on one effort of method development that occurred during my PhD project, and that has to do with ab initio phasing. So my major project was on this virus called canine parvovirus. And it was a collaboration with multiple lab members at that time, in particular Zhao, who was a student a few years senior of me. She really spearheaded the structure determination of the full particle, and I learned with her at the same time, where later on I led the effort on structure determination of the anti-capsid. So parvoviruses are negative sense, single-stranded Dengue virus, and they are pathogenic both in human and in animals. So CPV is quite interesting. At the time, it was a new virus. And why is it a new virus? Because it was emerged likely from a relative in feline, in cat, which is called the feline pan-leukopenia virus. So the virus was identified in 1978 and quickly became pandemic. Now you can find infections of CPV in all populations of domestic and wild canids. Everything that has been examined have this trace of infection. And there's really only a few mutations that's mapped to the capsid protein that's responsible for this adaptation to replicate in dogs. So in preparation for this talk, I went back to read some of our old papers. Fortunately, I still find them to be quite interesting, especially in the part of structure determination. And I think the CPV structure determination really represents many of the elements that has been said already, but also is an ultimate example in the power of molecular replacement averaging. So I will tell you a little bit more detail. But here are some of the basic data on CPV and their crystal. CPV is the T equals 1 virus. It's fairly small and very simple. The virus was crystallized in the P2-1 unit cell, shown there. Data were collected at synchrotron with fairly small oscillation angles with 1 virus per asymmetric unit. So that's actually a key because you now have 60-fold power of averaging. Also very low resolution data were collected. So you can see in the next slide that the low resolution data was important in the structure by moving the crystal to the detected distance to a longer one, then you can you don't have to block so much of the low resolution reflections. So crystals were randomly oriented. This I think has not been mentioned, but this is the so-called American methods, and that gives challenge to how you may be able to index these randomly oriented diffraction patterns. So this was also developed at least partly at Purdue by Sang-Soo Kim under Michael's guidance. And then this refinement of crystal orientation, intensity measurements, scaling, post-refinement, and averaging of symmetry-related reflections were all accomplished with the local program that Michael wrote. So later on, both of these two things, indexing and data processing, were all part of, I would say, the basis for more modern data processing software, such as HCAL 2000 or 3000 at this point. So here I summarize how the structure of CPV was determined and how this ab initio phasing was entered into the equation. So the crystal shown there is the P21 crystal. In order to do molecular replacement averaging, of course, you have to first look for the orientation. By the rotation function, the two-fold, three-fold, and five-fold were identified, and it turned out that the two-fold was very close to the crystallographic two-fold, which is the B-axis. So this will come to the next line there. So Michael was also able to take these symmetry axes and fit them into an ideal icosahedron. This way you can refine the parameters a little bit better. And then once you have a rotation, of course you also need to do the position. So in this case, since we don't know how the virus should look like, but one may be able to approximate a icosahedral virus as a sphere. So by looking at the packing of spheres in the crystal, you can just randomly search and then see which one fits. So it turned out only this position at x equals around a quarter, and y of course is arbitrary, and z also equals a quarter. That's where the particle has to sit. And then this position was further refined using Nathan-Patterson, and this is because the two-fold was parallel to the crystallographic two-fold, or close to parallel, so you get additional peaks in this Nathan-Patterson. And the other thing that they did, we did, I feel like I'm not responsible because I was really just learning for this project. So we fit the low resolution data with a variation in the inner and outer diameter of the sphere. And the best fit went to an outer radius of 128 angstrom and or 122 angstrom, both fits, and the inner radius of 85. So because 128 is sort of more similar to the 129 obtained from the other methods, we started doing phase extension using 128 and 85 as the spherical model. It's really no model. You just start with the sphere. By calculating phases at 20 angstrom, it was then extended slowly, one reciprocal space point at a time, to 9 angstrom. So in this process, and also in the later phase extension process, the Purdue University Supercomputer Center was also a big help, and all of us, the students, had experience to learn how to do vector programming, so that to utilize the power of those supercomputers. So by the time the phase was extended to 9 angstrom, the agreement between the calculated structure factor and the observed structure factor was so poor that they could not further extend anymore, so they were stuck there. And then we had this data of platinum. Only 5% of data were collected. So please remember, this was before the age of freezing crystals. So 5% of data required many crystals, in fact. So even with just the 5% data, a difference Fourier using the phase starting from the spherical model generated a difference Fourier that revealed the position of the platinum. However, this position of the platinum is not at the positive peak, but at the negative peak. So that suggested that the original phase obtained at 9 angstrom was shifted by 180 degrees. So retro retrospectively, later on after we solved the structure, it turned out 122 was the better estimate. So had we used the 122, we would have been able to extend all the way to atomic resolution. So then the platinum positions, because you have 60 of them, right, and the center of that should be the virus position. So those positions were then also used to refine the virus position. And then the single isomorphous replacement phase, which is only 5% at 8 angstrom, was calculated. And then it was just such a poor starting phase, but then through phase extension, using one reciprocal space point at a time, we were way to 3.25 angstrom, and showing there is the structure. How am I doing the time? Yes. Okay. So with Jack said about this light box, that's also what we did with CPV, and of course, no time should be wasted. So we, immediately the students made those transparency stacked box, and we spent the whole night to trace the molecule. Okay, so let me just say a few words about influence, at least on my personal perspective of a lifetime. So I feel we're really extremely fortunate to be a student of Michael. Michael really worked extremely closely with us. We learned so much about everything from him, and he was generous, sending us to meetings, to collaborators to learn how to do things. This was my first project, cauliflower mosaic virus. The crystal only diffracted to about 20 angstrom, but from that I learned how to do wet lab and things like that. So upon Michael's passing, some of our former trainees have started to write memorial pieces about Michael, and please check them out. And I think we should let Michael's legacy continue by doing good work and enjoying the process. Thank you very much.
Thank you. Okay, our next speaker is, I remember those negative names.
You do, right?
I do, yeah. I was mystified.
Yeah, exactly. I didn't want to use the word.
It's Ray Zhao, and Ray Zhao is from the University of Colorado Medical School.
All right, so I was a graduate student in Michael's lab from 1992 to 96, and there I was, I think this was 94 probably. So I'm going to talk about a little bit about Michael's scientific legacy that's related to the work I was doing when I was a graduate student. And also I will end with some reflection of Michael's influence on people around that period in Michael's lab. So I did my second rotation in Michael's lab, and the first thing I did was to process these rhinovirus data that was collected as oscillation photographs on films. So nowadays, essentially all protein diffraction data are collected in oscillation mode. But at one point, instead of oscillation photograph, the precession photograph was actually the main method of data collection. So if in the oscillation method, basically you take multiple still photographs, and then you adjust the orientation of the crystal so that one of its main axes is parallel to the X-ray beam. And then the crystal is basically moving in the precession mode, and so is the film. And this way, the data collected on the film is basically one reciprocal lattice plane without any distortion. So on the bottom here is an example of precision photograph of lysozyme. So you can clearly see the four-fold symmetry. So it is really easy to index a precision photograph, but it is probably not the most efficient way of data collection. So in the 70s, there's a movement of reintroducing the oscillation method as data collection method. And this posed a number of challenges, and Michael made major contributions in resolving these challenges, and these also contributed to their success of determining a lot of the virus structures. So in the oscillation method, basically the crystal is oscillating in a small angle, and the reciprocal lattice points that hit the Ewald sphere are not necessarily on the same reciprocal lattice plane. The challenges, the First is how you basically determine crystal orientation, especially for those crystals that are radiation sensitive. So you really don't have time to set crystal to a particular orientation. So as Zhao has mentioned, Michael and his colleagues basically developed what he called the American method. You shoot first and you think later. So basically they first developed this method of you take the oscillation photograph and then you take two orthogonal still photographs to use that to determine orientation. And then when they started working on Dengue virus, the challenge was even greater. These viruses, the crystals of these viruses are so sensitive. You get one beautiful oscillation photograph, and then after that, the crystal is completely dead. You don't even have a chance to take a still photograph. So with that, they had to develop a method to basically determine crystal orientation from a single oscillation photograph. On the left, there is a schematic representation of oscillation photograph, basically using the reflections in these loans and the relationship between these different loans within a zone. They were able to determine cell dimensions, crystal orientation based on one single oscillation photograph. And this, of course, nowadays is standard practice for almost everyone. And in trying to process these oscillation data as accurately as possible, a lot of the concepts and approaches Michael developed, like Hao mentioned, have now become basically, they are either directly used or adopted in many of the popular data processing software everyone uses nowadays, like HKL and MOSFET. Some of the concepts, for example, in profile fitting of in reflection box, or what we call shoebox in the lab, and his approaches of how to deal with refining crystal orientation, the crystal setting parameters, how to deal with partial reflections, error estimation, reflection rejection, and scaling. A lot of these are used in the modern data processing softwares. And these technical developments played instrumental roles in helping Michael's lab determine the virus structures, including what Eddy mentioned, the first animal virus structure, the human rhinovirus structure. So my thesis project was on one of the over 100 rhinovirus serotype, is HRV3. So before I went to graduate school, I used to get cold a lot, catch cold a lot. For whatever reason, in graduate school and after graduate school, I rarely did. So I rarely got cold. And so Michael used to joke about that, saying that it's because all the rhinovirus serotypes I got exposed to in the lab. But truth to be told, it's probably because America is so much cleaner than China. But anyways, so on the left here is a schematic representation of icosahedral rhinovirus. And so in the middle there, this triangle is from 5-fold to the 2-3-fold. So this is colored based on the distance of an atom to the center of the virus. And so the colder color has a shorter distance. So you can immediately see that there is a depression or canyon surrounding the 5-fold axis. So Michael reasoned that this is the canyon. So this canyon might be the receptor binding site. So Eddy also mentioned this. And because of the narrowness of the canyon, most of the antibody wouldn't be able to get into the canyon. So the virus can basically mutate all the residues outside the canyon to escape host immune surveillance without affecting receptor binding. So this is the so-called canyon hypothesis. And so around that time, Roland Ruckert and Barbara Sherry, Michael's collaborator at Wisconsin, have identified a lot of rhinovirus mutants that escape the monoclonal neutralizing antibody. So they have come down to Purdue to map these mutants to the newly solved HRV14 structure. So the story, Michael has related the story multiple times. So the first few mutants they match perfectly to the canyon hypothesis. So Michael got so excited and so nervous that he said he couldn't stand it. He had to basically leave the room. So by the time he calmed down enough to come back to the room, the team has mapped all the mutants, and it actually matches the canyon hypothesis perfectly. And the candy hypothesis was also later confirmed by the CryoEM structure of the receptor of the rhinovirus with the receptor. And also, as Eddy mentioned, in collaboration with Sterling Winthrop, later biopharma, Michael's lab has also demonstrated that small molecule compounds like these wing compounds can bind to the capsid of the virus and stabilize the capsid protein and prevent the virus from encoding. And these compounds actually were successfully developed into anti-rhinovirus drugs. Unfortunately, it was not approved by the FDA, mostly due to complications in women using birth controls. And so with that, so these basically are just, a short list of the long list of Michael's scientific achievement. And in addition to his, obviously, scientific accomplishments, one of Michael's legacies are the scientists he trained. And so one of the things that I'm still in awe even today is that, he, at least during that time, he would sit down with every one of us and go over our thesis word by word. And I probably learned more about scientific writing doing that with Michael than any classes I took. And Michael also had a lot of international students, and for a lot of us, the Chinese students around them, we couldn't really afford the time and expense to go visit our parents very frequently. So Michael and Audrey basically became our surrogate parents. So a lot of us learned how to drive when we were in Michael's lab. So when we went somewhere together by car, he would have us drive, and he will critique our driving. Although I'm not so sure about Michael's own driving skills. So a lot of us have gone skiing, sailing, hiking with Michael, and Michael has met our parents and has held our babies. This actually was my son when he was 2 months old, and I have another picture, I forgot to put it on here. When he was 18, Michael was trying to explain his paper to my son. And Michael even held wedding ceremonies for some of us. And so I think Michael probably wasn't the most patient and diplomatic person at times, but I think he genuinely is interested and cared about people he have crossed paths with. And I think I can speak on behalf of many of us who were in the lab during that time, that we were fortunate to be trained, to have trained and worked with Michael. And it is our hope that in ways, big or small, that we can pass on Michael's legacy in the students and postdocs we train and the people we work with. Thank you.
I had no idea he taught all those students to drive. It's a little scary. You ever saw Michael drive, that's scary.
He said if you can't drive, you can't graduate.
You can't drive. You can't graduate. I only make people know how to open a bottle of champagne. So our final speaker this evening is Saif Hassan, who is a recent alum of Michael's lab, possibly the most recent one to have a faculty position, and he's at the University of Maryland.
Okay, so I was a postdoc with Michael from 2013 to 2019, and I was not supposed to be a postdoc with Michael because I'd done my PhD also at Purdue with Bill Kramer, working as a crystallographer. And I'd gone to meet Michael because I'd taken his crystallography course, and I wanted to do EM with Jack Johnson. And I'd gone to Dr. Michael to learn a little bit about EM, and I said, Michael, I want to learn about EM. And he said, why? And I explained to him, and he said, who do you want to work with? And I said, Jack Johnson. And his response was, why? Long story short, I walked into Michael's office to learn about CryoEM. I walked out of his office as a postdoc. Anyway, so today I'm going to talk about, very briefly, about Michael's contributions to hybrid methods that he not only developed, but also used to successfully interpret the structure of the dengue virus. So why was Michael really interested in the dengue virus? Dengue is a flavivirus that is commonly transmitted by mosquitoes, It causes a variety of symptoms ranging all the way from mild fever to hemorrhagic shock and death. And in the early 2000s, dengue had made a very large-scale comeback in the Americas. It culminated in 2002 with a Pan-American outbreak with over 1 million cases that were reported. The mature infectious form of the virus has the envelope protein on the surface, which is a major target of neutralizing antibodies. A crystal structure of a related envelope protein from TBEV, also flavivirus, had been determined a few years prior by Felix Ray and Stephen Harrison. However, with all these outbreaks going on in the early 2000s, there was still no structure of the mature infectious virus. With this background, Michael was part of a collaborative effort of researchers between Purdue and Caltech who determined the first ever structure of a mature infectious flavivirus. These researchers used CryoEM to a resolution of 24 angstroms and determined the first structure of the dengue virus. It was left to Michael to interpret this virus structure. Shown here is a CryoEM map of the dengue virus at a resolution of 24 angstroms. At this resolution, this icosahedrally averaged map is nothing but a smooth, featureless golf ball. There are no major spikes on the surface, which makes the interpretation of this map extremely challenging. But then Michael never met a challenge that he did not like. So he jumped head on to tackle this problem. In the first step, Michael and his colleagues calculated a radial density distribution of the dengue virus map. This allowed them to find the envelope protein layer at a distance of 245 angstroms. This is colored in dark blue. Then Michael cut a very thin section of this dengue virus map around the 245 angstrom distance, as shown over here. This triangle represents an icosahedral asymmetric unit. This map at a resolution of 24 angstroms looks like a jumbled mess that would be hard to interpret. That is to everyone except Michael. When he looked at this map, he recognized one feature immediately, which I've highlighted here in white and red. This shape immediately reminded Michael of the shape of the envelope protein dimer that had been crystallized by Felix Ray and Stephen Harrison. So Michael's next task was to fit this dimer into the CryoEM map. But this was the early 2000s. Interpreting CryoEM maps was mainly done by fitting crystal structures into the map by hand. According to Michael, this method of fitting crystal structures by hand was subjective, inaccurate, and now I quote Michael, ignorant to the power of n, where n stands for ad nauseam. Yeah. So, frustrated with the lack of technology, but more probably nauseated by the lack of tools, Michael did what he did best. He used 2 fingers and a type relief. Kara, who drew this picture, is in the audience right now. Enter EM Fit. Michael wrote this program to fit crystal structures into CryoEM maps. This program works on 3 basic principles. This program tries to maximize the number of atoms fitted in regions of high density, minimize the number of atoms fitted in regions of low density, and minimize the number of clashes between symmetry-related molecules. Once Michael had written this program, he used it to interpret the structure of the dengue virus. He first placed an E protein dimer that I've colored in yellow onto an icosahedral 2-fold axis that I've colored in red. He then rotated and translated the dimer along this axis while maintaining the dimer 2-fold axis always parallel to the I2 axis until he found the best fit. He did this experiment a total of 4 times. In the first attempt, he took the map as it had been calculated and placed the dimer the way I've shown over here. In this second experiment, he took the same map, but then flipped the dimer upside down and repeated the fitting. In the third and fourth experiments, he inverted the hand of the map. By comparing the top fits obtained from each of these experiments, Michael was able to find the best overall fit. This fit had a relatively high average electron density score, which is shown as sum F, and a relatively small number of atoms in the negative density region. Shown here is the best fit of the E protein dimer as obtained by Michael. Not only did the coordinates fit well, but Michael was able to fit even the holes of the dimer pretty well with what had been determined in the map. But once Michael had fitted this dimer into the EM map, he noticed a large volume that had been left unoccupied. So, as the next step, Michael reset the values of all the voxels that had been occupied by the icosahedral dimer to a value of 0, leaving behind only the unoccupied volume. This volume again reminded Michael of an E protein dimer. However, the 2-fold axis of this dimer was non-icosahedral in position. So, Michael proceeded to fit the second dimer into the asymmetric unit. This time around, he constructed a quasi-twofold radial axis that I've shown in blue. He placed a dimer onto this axis while maintaining the dimer twofold parallel to this Q2 axis. He then rotated and translated the dimer until he obtained the best fit. Because this axis was only approximate, Michael also refined the orientation of this axis. Shown here is the best fit of the general position dimer highlighted in yellow along the quasi-twofold axis. This structure, which consists of two general position dimers flanking a central icosahedral dimer, would later on be known as the raft. And in retrospect, it is almost ironic that the structure should be called the raft when the gentleman who discovered it was a passionate and proud sailor who would have nothing to do with a life-saving device like a raft. So, this is the final structure of the dengue virus as interpreted by Michael Rossmann. When Michael first tried to publish this paper, it was rejected by Nature and Science with the comments that Michael did not know what he was doing. 20 years down the line, we now know not only was Michael right back then, working with a relatively low resolution, but that the principles that he got by determining this structure are true even for other flaviviruses, including Zika, whose first structure was also determined by Michael's group. This latest discovery from Michael's group was important enough that the NIH held an announcement on the website and later on held a news conference. Working at a relatively low resolution, Michael was able to get this information out, which holds true even to this day, because he had a deep understanding of symmetry and truly believed that these viruses had icosahedral symmetry. This concept of icosahedral symmetry was truly a guiding principle of his career, and because Michael was a man of strong principles, and because he believed in icosahedral symmetry, he then went forward and published a paper saying flaviviruses do not have icosahedral symmetry. So much for Michael's principles. So, I'll end my talk by showing you this photograph of the lab in September 2018. The reason why I'm so happy in that photograph is because I'd just been offered a job, and so I knew I would not have to run and fit in it. Yeah. Because this is a crystallography audience, I expect most people have already recognized the gender symmetry distribution in this photograph. This was no accident. Michael was orchestrating all of this. Again, because this is a crystallography audience, the fact that there is gender symmetry or symmetry of any kind on either side of Michael means that Michael sits and overlaps in position with a symmetry element which gives him a very well-deserved special position.
That was fantastic. Thank you, Saif. So, wow, that's quite a legacy. Turn this thing up before it brings me out. So, thank you, all five of you, Jack, Eddy, Hal, Ray, and Saif. Those were wonderful talks, and this was a beautiful summary of Michael's career in the last 40 or 50 years, something like that. So please join me in thanking all of our five speakers.